Hi, my name is Ian Fogarty, and I'd like to talk to you today about polar molecules and dipole-dipole intermolecular forces. We already talked about one type of intermolecular forces, the van der Waals forces or London dispersion forces. They occur in all molecules and are particularly predominant in non-polar molecules like octane. Suppose we have a molecule here, and one of these atoms is very electronegative and one of them is not. Let's make the electronegativity of the gray one somewhere around 3, and electronegativity of the pink one somewhere around 2. That means the difference between those two is going to be 1, and that's going to place it in the polar covalent. So this is a one polar covalent molecule. Here's another polar covalent molecule. What that means is the electrons that are in this atom right here are going to spend less time around this atom and more time this way. It's going to be polarized this way. And I'm going to end up with a partial positive on this end and a partial negative on this end. Well, we have another identical molecule up here. The same thing's going to happen, and so we'll end up with a partial positive here and a partial negative there. Now, this is called a dipole. It has one pole, another pole, and so it's a dipole. Polar molecules have dipoles. This pink atom right here that is partially positive and a little bit electron deficient could be orientated near this one that's got extra electrons, and there can be attraction there. So there can be attraction between here and here, and likewise between here and here. And so this is going to be an attraction between two molecules, so it's intermolecular force. It's between one dipole and another dipole, so it's called dipole-dipole. It happens with polar molecules. So if we look at a water molecule, we have the electronegativity of oxygen being 3.5, and electronegativity of hydrogen being 2.1. So electrons that are in this bond will spend more time around the oxygen than around the hydrogen. That will leave a partial positive on the hydrogen and a partial negative on the oxygen. So we have a polar bond, and it's a dipole. We have the same dipole down here, a partial negative and a partial positive. And it turns out that the partial positive of this hydrogen can be attracted to the partial negative of that oxygen, and so we'd have a dipole-dipole interaction. However, there's something very special about hydrogen, oxygen, and nitrogen. Here you have an oxygen, hydrogen, oxygen kind of sandwich happening, and so this is particularly strong. It's a dipole-dipole interaction, it's true, but because it's oxygen, hydrogen, oxygen, it's particularly strong, and we call that hydrogen bonding. And hydrogen bonding is responsible for many of the reasons why our body behaves the way it does. It has impacts on the way proteins fold. It's one of the reasons why DNA twists the way it does. It's why water freezes and floats, and why we can have life in water in the winter. So if you have an oxygen, hydrogen, oxygen, or an oxygen, hydrogen to a nitrogen, or a nitrogen, hydrogen, nitrogen, any of these kind of situations will result in a hydrogen bond. And they can be particularly strong. They are the strongest of the intermolecular forces. In fact, sometimes it's hard to tell, does this hydrogen belong to that oxygen, or does it belong to that oxygen? Sometimes it's hard to tell. Hydrogen bonding in alcohols. So here we have an alcohol and another alcohol and another alcohol. And we can have our polar bond right here and a polar bond right there. And what that means is that we would have a hydrogen bond to that one and a hydrogen bond to that one. Now it's true that we can still have our non-polar London dispersion bonds between this alcohol and that alcohol, but between this alcohol we can have a dipole-dipole, or in particularly hydrogen bonding. So if we review, when we looked at alkanes, we started out way down here with one carbon, and the boiling point kind of did that. As the molar mass increased, the temperature of the boiling point goes up because you had more London dispersion forces. What does that look like for our alcohols? Well, our alcohols, they follow a very similar trend, but everything is raised up a little bit. Alcohols still have all the same London dispersion forces that the alkanes had, so you have this kind of curve that gradually increases. But in addition to that, you also have hydrogen bonding with the OH, and so everything is raised up a little bit. Thank you very much for your time.